All right, friends, let's go through our steps to use the quadratic equation to solve for our unknown variable t when none of our inputs are 0. So we started with the equation that you see highlighted in yellow. Delta y equals Vy initial delta t plus 1/2 Ay delta t squared. Now, usually what happens is that either delta y or Vy initial is 0, and so one of those terms will drop out from the equation, and we would have a nice and easy time solving for delta t. Now, in this particular case, none of our inputs were 0. And so we have a situation that encourages us to use the quadratic equation to solve for delta t. If we move delta y from the left side of our equation to the right, then we see that we have an equation that is in standard form. Now, standard form is characterized as ax squared plus bx plus c. So this is the first thing that you need to pay careful attention to when using the quadratic equation. We absolutely need to have a plus c term in order to use the quadratic. So I'm looking right here at the plus c. Now, when you look at our equation, 1/2 Ay delta t squared plus Vy initial delta t minus delta y, you'll see that this is why we have to include the minus sign with the delta y. It has to become part of term c in order for us to kind of put this imaginary plus sign, which I'm coloring in right now. In order to use the quadratic equation, the equation has to be in standard form, which says that it has to be ax squared plus bx plus c. So we need to make sure that the negative sign always follows or is included with the delta y term. Otherwise, you cannot use the quadratic formula. When we list out our coefficients and our constants, that would make capital A, the coefficient capital A, equal to 1/2 acceleration in the y. Coefficient B would be equal to Vy initial, and constant C would be equal to negative delta y. So I'm just going to emphasize the fact that there is a negative delta y and that the negative sign must be included in your constant. If we rewrite our quadratic equation, x equals negative b plus or minus square root b squared minus 4ac over 2a, if we rewrite that equation using our physics variables, we see that delta t is equal to negative quantity Vy initial plus or minus the square root of quantity Vy initial squared minus 4 times 1/2 acceleration in the y times negative delta y. That entire quantity is then divided by 2 times 1/2 acceleration in the y. When we plug in our inputs, so here's our variable table, we've written out our inputs. Remember that we measured delta y with the meter stick. When we plug in our inputs, we can see the equation rewritten as this. So we see that we've plugged in Vi sine theta as our Vy initial. We're plugging in negative 9.81 meters per second squared as acceleration in the y. We're plugging in a positive 0.832 meters as our quantity negative delta y. And if you have any questions of that, you can see that we've written that here in red. Because the delta y quantity was already negative, when we take the opposite of that, that's how we end up with a positive 0.832 meters. Now at this point, you want to be very careful how you're entering these numbers into your calculator. Most of the mistakes that happen as students use the quadratic equation is because of dropping negatives by accident or forgetting to square certain terms. So we must always mind our details when we're using the quadratic equation. When we plug these numbers into our calculator, I'm just going to highlight in orange. this entire term here of 4 times 1/2 times negative 9.81 times a positive 0.832 meters becomes what you see in orange here. The 3.3279 meters per second, our Vy initial, becomes the 11.0749 meters squared per second squared. Now notice how this negative sign, which I'm about to circle in red, this negative sign is still present. I haven't yet included it in my calculation. And when I calculate the discriminant is all of the numbers that are under the square root sign. When I calculate the discriminant, and I'll highlight that in purple, that is equal to 27.399 meters squared per second squared. Now you'll see that right now for this particular tutorial video, I'm doing some rounding, but when I'm actually calculating these values and plugging them into my calculator, I do not round at all. So I'm either entering it at one time as one calculation, or I'm storing my values in my calculator for later use, but I'm not rounding as I go. Now in the denominator, we see 2 times 1/2 times negative 9.81, and the 2 times 1/2 becomes 1. So 2 times 1/2 is equal to 1, and so right here I've just crossed them out. So really my denominator is just negative 9.81 meters per second squared. Now right here, this is a hint as to what sign you need in your numerator. Delta t cannot be negative, and so if our denominator is a negative value, we are looking for an option that makes our numerator negative as well. Right, we're looking for a negative numerator because our denominator is negative, and delta t cannot be a negative value. When I take the square root of 27.399 meters squared per second squared, I end up with 5.234 meters per second. So notice how the units go from meters squared per second squared to meters per second. So the square root also applies to the units, not just the number. Now this is the point where we need to discern, are we adding a positive 5.234 meters per second to our initial y velocity, or are we subtracting 5.234 meters per second from our initial y velocity? So let's explore these two options. Remember, we have a negative 9.81 meters per second squared in our denominator. So we're really looking for that negative numerator. With option 1, so I'll just put a 1 right here, we see that if we choose a positive 5.234 meters per second in the numerator, we will get a positive numerator. And with option 2, if we subtract 5.234 from our negative 3.3279 meters per second, we get a negative numerator. So the two delta t's that we end up with are either delta t equals negative 0.1943 seconds or delta t equals positive 0.8727 seconds. Now remember that delta t can never be negative, so this is not an option for us. So that's how we know that this delta t is correct, and remember, you will only ever have one answer. You will never use the quadratic equation and get to the end of a problem and see two options for delta t that both work. Or hint, at least not yet, but we'll save that for another day. Now let's just double check. So using the quadratic formula, we got a delta t for our projectile of 0.8727 seconds. And if we scroll back up to our work, from the many-step method that you see above that we did in class, the delta t that we got, 0.8727 seconds. So you see that you get the same answer, whether you do the multi-step approach And remember, the multi-step approach breaks the problem into two different periods of time. One period of time where we're looking at the muzzle to the peak, and the next period of time where we're looking from the peak to the ground. So this is the multi-step approach. In the multi-step approach, we got a delta t of 0.8727 seconds. And with the single step approach of the quadratic equation, we get a delta t of 0.8727 seconds.